صباح خير. شحال
عندك لي زيربونت
كنت تعمل مزيان.
اي بيان سور با دو سوسي جوست حط لي اون
ما عندكش نتاع البروجيكت نتاع لي سلايدز اللي يعدي وايرلس؟
هو هذا يعدي
واير
نورمالمون t'as besoin de quelque chose ici oui non ça non
on n'aura pas besoin, il faut installer quelque chose.
انا مثلا انا يعني une petite carte qui est intégrée في
تعال نشوفوا بريكسي تمشي. attends انا اوكي il faut que je fasse لطيف.
ولا يركب هذيك قبل ياخذ الجميع
مشيت.
كوم سي هذاك جماعة نحكي عليه خاطر
انا في il a un peu exagéré mais فما اللي راقصات هذوك فما
c'était acceptable enfin il y en a qui étaient acceptables
elles étaient acceptables مش كيما نتاع الصيف يبدا فريمون. اما انا ما شفت انا عطيتهم بالظهر.
لا انا والله الا نقول خاطر مادام ناخذ بينا نحكي ونمشي نسهرنا شويه
خير. اما الماكله باينه جابوا قهوه سيتي با مال. دونك فوالا attends سنة نعمل attends هو باش كذا لا انكور ديتيكتي نشوف
وتعمل لك الكنترول.
الماك مختار ماك سي ديفيرون. لازم نشوف
Oui, pas de signaler là par contre. Oui, le Mac rire en fait. La vidéo là, je pense à basculer.
Mac أحسن.
Je bosse sur Linux depuis.
Detect display, ça. Il va détecter.
Voilà.
C'est bien.
Voilà. Va bien.
نشوف تاع الباوربوينت. انت بادي باوربوينت
Oui, ça doit aller.
كيف
Oui. Bon, ça pointe, ça c'est sûr. Ah, tu vois. C'est que peut-être il y a en fait la carte réceptrice-allemande où elle n'a pas été activée.
Ah.
Mais bon, ça te permettra au pire d'utiliser le. Mais c'est.
أنا عملته.
Oui, عرفت فهمتك. ماشي كيفاش خاطر الماك دابيتود كلهم.
الماك سي بارتيكولي سي.
بون فوالا.
ميساج على الأقل عندي على الأقل ميساج. دوك بوينتر.
البوينتر هذاك الفيفوريت. أي.
Évaporation. لو Sup'Com عالم أمريكي. ربما قال شكون عمل هذيك الزويات ولا
أبدأ. أوكي.
خليهم كلهم في الواحد. Tu commences par des généralités. بدك بارصة في دون الكويس.
De la radio, application dans les réseaux ad hoc. Donc,
thank you very much for the kind invitation. This talk will be about cognitive radio wireless ad hoc and sensor networks, CRAN. And first of all, I'll say a few words about Queen's University. Queen's University is in Kingston, in the province of to cover I'll start. We had a very beautiful introduction yesterday by Professor Awatif, and I'll try to present it my own view. Cognitive radio networks which are actually essential. I probably spend 40% of the time on this because it's important to understand it. And then we move to the actual topic, which will introduce ad hoc and sensor networks, and then we'll try to see the challenges, and we'll focus actually, in this talk I will focus on two main issues. The first one is fairness, to be fair when you share and allocate the spectrum bands. And the second point is medium access, how we can access the channels. And of course, we have all the challenges, mobility, power challenges, etc., multi-hopping in cognitive radio ad hoc networks. So, and of course, I will not forget the conclusion at the end, okay? So, because we had a discussion this morning about conclusions. So here, to give you the picture of sensor networks, you have in this diagram here a wide variety of applications of sensor networks. So we have, for example, in smart homes, you can build your own sensor network to monitor the energy, to monitor the lights, to monitor, for example, the fridge, every appliance in the house you can monitor it, and then be able to control your dishwasher, to program it, for example, stop it, etc. We have, for example, environment monitoring. Forest monitoring, we deploy sensors in a given environment, and then we collect data to measure the environment and, of course, try to make decisions about that environment. We have water quality monitoring. This is also a new field of research, which means that the water distribution system can be monitored wirelessly, so you can, you know exactly how water is consumed by people, how water is distributed, if there are any leakages, any problems in the water distribution network, and optimization of water and energy, because when you deliver water to people, you will consume also energy to pump the water, to distribute it, etc. So that's important to have a monitoring system based on wireless sensor networks for that. You have the smart grid. So in smart grid, which is smart power grid, the electricity grid, you can have smart meters in every house. And in the house, you will be able to measure your own consumption as a consumer, but also the utility company will be able to read your consumption in real time. So every second, your consumption will be known by the power company. So you will not be able to cheat. You will not be able to make any changes to your consumption. This is one hand, which is good for the company, but for yourself, the company, by having smart meters, they can actually make a pricing according to the time of the day you have consumed electricity, the same as the telephone, okay? In the telephone, we deal with packets, we deal with transmission of information, so we know exactly what we have consumed in terms of the telephony system. Here, in the smart grid, it's the same thing. So we know exactly when people have consumed, so if there is a peak time, for example, we know the peak time of the day, for example, between, for example, 10 o'clock in the morning and 2 o'clock in the afternoon, then at that time it will be a red pricing and the prices will be very high. In the morning and late afternoon, for example, the prices will be average. And of course, at night, the prices will be very low. So in that case, the power company, they can actually manage the power better. And you, as a consumer, you can actually choose the time of the day which is the cheapest for you. Now, for the smart grid, there are a lot of problems. One of them is the huge amount of data that has to be transmitted. So we have imagine every smart meter in every house, how many millions of houses there are. And also buildings, government buildings, etc., which are important. We have also electrical vehicles that can be used because we have a smart grid. Also, the power company, they can actually install meters everywhere in the distribution system. It's not only in the houses, but in the distribution system, so that they can control the distribution of electricity, so that they can actually provide the exact amount of electricity to, they generate the exact amount of electricity which corresponds to the demand. What's important in the smart grid is that the electricity grid, which is important, is that the demand should be exactly equal to the offer or the generated electricity. If there is an unbalance, then there will be a lot of power losses. So if you deploy nodes throughout the distribution system, which can be of millions of nodes, in every generator, in every line, when necessary, we'll deploy these sensor nodes. You can get that feedback to the company, to the generators, and the generators will actually control and adapt their generation according to the digital information that comes to them. So we have actually analog, or let's say power, in terms of control of the grid. You have the power control in a loop, but also you have the data that comes throughout the whole grid, that comes wirelessly in real time, that will influence actually the generation of electricity. So we have a better and more accurate control of the grid. And then you have city pollution monitoring, so you can deploy nodes in a city to control the pollution. You have healthcare, so body area networks here. And then you have the Internet of Things. So the Internet of Things actually is very general, so it can be based on, for example, RFID, radio frequency identification systems. It can be based on sensor networks, it can be based on ad hoc networks. So it's actually, it includes everything, and it's actually a generalization of what we can do in terms of sensor networks and RFIDs. So the Internet of Things, one of the technologies which is actually used is energy harvesting. So you want to have a tracking, for example, and identification of every item, of every object in the world. So in that case, you don't want to have a lot of, what you want to have is to have renewable batteries, or simply a system which is self-sufficient in terms of power. So in that case, energy harvesting through, for example, electromagnetic signals, for example, can be a good choice. It can be also through solar cells. It can be through many ways, actually, to be able to have millions of objects which are actually monitored, but without actually any external energy that has to be plugged. So here we have, of course, many challenges. If you want to have an autonomous system, a system which is mobile, because in many cases we have users that are mobile, we want the system to have a lifetime as long as possible. So lifetime, for example, in if you consider, for example, pollution monitoring, the lifetime of the system has to be of several years. If you consider, for example, the smart grid, for example, of course, the lifetime has to be also of several years, so don't want to change your meters every month or every week. In the Internet of Things, we have the problem of mobility, so we have to deal with that as well. So there are a lot of challenges that we have actually to manage. And this has to be through many approaches. So we have seen yesterday cross-layer design, which is actually a very advanced and also under development, but I will actually criticize it a little bit, okay? Actually, cross-layer design has not been even established yet, and people, they started criticizing. So it's not me, but this is actually what we found in the literature, but people actually try to sell the cognitive approaches. So cross-layer design, of course, is very good. As I said, it's not yet implemented, and many people are working with that, which is really very good. So I'm not saying that it's not a good technology. However, just to show the general framework that cognitive approaches can offer. And cross-layer design can be seen as a special case of cognitive approaches. The first thing is that cross-layer interaction is limited usually to some layers. So what we see in research is that people actually, they consider, for example, physical layer and the MAC layer alone, or the network layer and the MAC layer, etc. So it's really very limited so far, even though the goal of cross-layer design is to include all layers in a seamless way and get rid of the rigid and strict OSI model. However, what we see today in terms of implementations are actually limited to some layers. And then the goals for the network-wide level, they are not really being considered. For example, in cross-layer design, what's considered is simply usually one special node or a node transmitting to another. This is where actually cross-layer design usually plays a role. However, cross-layer design doesn't have a vision for the end-to-end goals of the whole network as an entity, as a complicated system. Okay. Cross-layer design also is usually reactive, so it reacts to some phenomenon to happen. For example, there is congestion, I will reduce the load. There is something that happens, there is need for power, I will add more power. There is more need for bandwidth. So it's really reactive to some problems. So we don't see that prediction or vision, long-term vision, especially at the network level. Reduced architectural modularity is still, it's actually still rigid in terms of functionality, and also we don't have the modular components that are clearly well defined. Also the high maintenance cost, which may apply also to other approaches as well. And then we may have some adaptation loops and instability. So this is, these are some criticism to cross-layer design. But as I said, cross-layer design has not been even established fully yet, and still in some limited implementations. But this is simply so people they start criticizing something without even seeing it actually flourishing and implemented. But anyway, so people are in rush, and that's what people try to sell. So these are not necessarily my own opinions, but they are actually opinions which are shared by a lot of researchers. So now, what's an alternative to cross-layer design is cognitive networking. Okay, so definition of cognitive approaches. We start with the cognitive radio. I think Professor Awad, she gave, I think, a similar definition. I think it comes from Heikin, Professor Heikin, who is in Canada, also in McMaster University. So it is a radio which is aware of itself and its surrounding environment. So there are two things, to be aware of self-awareness and awareness of the environment. Capable of adjusting its communication according to stimulus from the surrounding environment, such that reliable communication and efficient utilization of the system resources can be achieved. So here the goal is actually to make the best use of the whole resources in the whole network. Okay, so how to do that? We adjust our parameters, our protocols, our designs, and so on. So that's actually what cognition aims at, is that to have self-awareness, awareness of the whole environment, and of course use that information to adapt, to adjust, to make sure that actually we are optimizing not only our resources, but also the resources of the whole network as a whole physical system. So that's actually initially what people started proposing. So for cognitive radio as a special case of the word cognition here, you have information that comes to the engine, to the cognitive engine. It can be a device, for example. And that device will receive, as I said, awareness from itself, awareness from the environment, and of course, any feedback, for example, from the receiver or any other nodes. Okay, and then of course it will adjust its communication parameters. Of course, the goal is to make efficient utilization of the resources, and of course it has to ensure that it has reliable communication with high data. So this is actually the goal of cognitive radio. Now, the spectrum awareness, it's very easy. So whenever there is a spectrum hole, as in the figure there, the cognitive radio will actually make use of these bands. So it's really very simple as a concept. It's not very complicated. And you have this cycle, okay? We talked about self-awareness, we talked about the environment. So what we need now is to sense the environment, okay? So that's why we have this, this cognitive cycle, is that you have the environment, you sense it, okay? So sensing, you will be able to learn what's going on in the environment, about the neighbors, about the self-device. And then planning, so using that information to plan, and after planning, you will make decisions. Okay, we say, okay, I will do this now, after that I will do this, etc. And as I said, for the network as a whole. And then actions, okay? You will actually implement these decisions into the environment. So the environment can be the other nodes in the network. It can be other networks. So it can be actually very, very general. But of course, when we sense the environment here, of course, we sense the physical channels. It can be even also the weather conditions. It can be the how many users in the network, for example, what kind of technology. If it is intelligent transportation systems, for example, the speed of the cars are important. The type of batteries used in electric cars, for example. This is important even for the communication system. Okay, it can play a role in that case. So the environment is really very general. And when we act on the environment, we can choose, for example, a different path as the previous one. We can actually allocate channels. We can change a lot of, we can even change the deployment of our nodes and its architecture. So it's really very, very general. Now, the concept of cognitive radio, actually, it has been generalized, okay? We no longer consider the radio devices as simply looking for a spectrum and then having access to the spectrum, but much more general. And this is actually what has been defined as cognitive network. So cognitive network is really much more general than a simple cognitive radio device. So what's a cognitive network? It is a network with a cognitive process that can perceive current network and environment conditions, and then plan, decide, and act on these conditions and in this environment. The network can learn from these adaptations and use them to make future decisions and, of course, improve and reach the end-to-end goals of the network. So here we are talking about the network. It can be any layer. It can be any object or any objective. And here the main important thing is the end-to-end goals of the network. Okay, so we have, for example, our goal to have a lifetime of a whole network of 2 years, to ensure that we have a mobility framework, to have applications, to have seamless integration between different devices and networks. So this is really end-to-end goals of the whole network. It's not end-to-end goals of a transmitter and receiver, or a group of transmitters and receivers. So this is really the whole network. That's how actually, or that's why the word cognitive network here is much more general than simply a cognitive radio device. Okay, so here we have to see that difference. Okay, so I was slow or fast, or how was it? Good? Okay. Any questions so far, or any remarks? Yes. Yes.
only for. Thank you. The bit rate, the SNR is not only for physical layer. It could be for a protocol or routing, as we have seen yesterday. So, as you say, this is the beginning of cross-layer design.
Yes.
And I agree with you that. For the moment, how it is used is limited, but
yes.
It's not said from what we say is that to make the layers collaborate and cooperate, and this is more large than what is done currently.
Yes.
And combined, well, you see it as a special case in the cognitive radio, but as I said, cognitive radio is coming from outside, surrounding environment, while cross-layer design is inside the network.
Yes.
So this is, I think that we need to make them collaborating, cross-layer design and cognitive radio, yes. to take advantage from all the information outside and interaction between different layers.
Yes,
that's
yes,
just
exactly.
a small comment.
Exactly. Thank you very much. So it needs this integration actually between the cross-layer design and the outside environment. Any remark or comment so far? Okay, so you can move on. So here, actually, one approach that has been made in cognitive networks is the concept of the knowledge plane. I think, as we have seen yesterday, for example, very well presented, actually. Okay, so. I think there is a problem with the slide here. Okay, so anyway, actually we have this layered architecture. Okay, you have the OSI model. Okay, as Professor Awatef said. So we have these 5 layers, for example. And then you have, especially in ad hoc networks and sensor networks, as we see later on, we have what we call the management planes. Okay, you have an entity, an engine in the protocol stack, which actually has a task to manage, for example, the power. Here we have, for example, power management, or resource can be seen also as a resource management. We know that an ad hoc network, so just to remind what's an ad hoc network, is simply a set of devices or machines which are ad hoc, which means that they don't have actually an internal infrastructure, it's infrastructureless, and then they communicate between each other. So I don't have the board today. We don't have the blackboard? We don't have it. Okay. That's fine. If we have, that's fine. If we don't have, that's okay. We have the blackboard.
We have the whiteboard.
Oh, the whiteboard is fine. Okay. You know, because sometimes you have some new ideas, or with the interaction, you need to write down something. Anyway, so here you have this. I was talking about the ad hoc networks. It's a set of people, devices that are in a given environment, and then they communicate together. They share information. They have applications, etc. So some of them may leave, some of them may stay, some actually can change their quality of service requirements. Some others, they can have different applications, etc. So this is actually a very, very challenging environment because it is time varying. It's unpredictable. The architecture, the infrastructure, as I said, is infrastructureless, but the deployment, everything is completely ad hoc and completely random. This is the case, for example, of intelligent transportation systems. Okay, ITS, intelligent transportation systems, are actually a very challenging environment. You have cars which are moving. You have people that communicate together. You have the cars that communicate together to exchange, for example, information about the speed, about proximity from a car to another. So cognitive. Of thousands people that are communicating. So here, the scale, we have to put in our minds that the scale is not simply a node transmitting to another node. It's actually a whole network. Okay, it can be heterogeneous as well. Okay? And it relies on tools of artificial intelligence and of representation of tasks. So this actually tools and techniques rather than simply allocation of tasks, do this or do that. Okay? والله يتعبناك سي سفيان بارك الله فيك. Okay, so your ad hoc network actually is composed of many nodes. So there are thousands of nodes. Okay, so they communicate with each other. They have any type of information, together. So this can be, for example, at time t1. Okay, at a given time you have this architecture. But later on, you may have some new nodes that came in and some others that have left. So you have the problem of mobility. Okay, so you have, for example, these ones are still there. Okay, but then you have some new nodes that came in. Okay, so you have the scalability, what's called scalability of the network. So network can be larger. And then probably some others that have left the network. Okay. So the problem here is that if for example, initially in the red network, if initially in the red network, for example, you have a communication between this and this to reach this, to reach this one, let's say. Later on, when your network changes, so there are some nodes that have left and some others that came in, you should find a route for your information somewhere else. So in that case, when it deals now with the new nodes that have joined the network, and still this node here needs to communicate with this one. So in that case, you will find another route, okay? So in that case, you will try to learn your environment and then follow this one, for example, this one, and then this one, okay? So this is what we call mobility management. You have changes in the network. At the same time, you want also to ensure that you have the quality of service requirements that are requested from you. And then, of course, here, as I said, the knowledge plane actually will allow you to optimize the whole end-to-end goals of your network. Now, the concept of cognition actually is very general, okay? And it has several levels. So let's actually start with the first level. So level 0, which is here. So it's the levels of intelligence, how intelligent your network will be, okay? Cross-layer design is a level of intelligence. Adaptive signal processing is a level of intelligence. Software-defined radio is a level of intelligence. So how can we characterize and rank these levels of intelligence? So first of all, you have level 0, which is pre-programmed. Okay? Your device is pre-programmed to do some specific tasks. If there is something as input, the output will be so and so. So we have, for example, pre-programmed modulators, demodulators, etc. So this is what we find in software radio. So it's really the basic thing of intelligence. And then we have the goal-driven, okay? We have a specific goal, so the design will be set such that these goals actually will be reached, okay? And therefore, we need environment awareness. So we need to know some awareness of the environment so that we can actually reach the goals that are set. But the goals, actually, we have goal 1, 2, 3, 4. They are predefined, okay? The goals are predefined. And then we have the context awareness, okay? We try, or the network tries to know what the user is trying to do, okay? Without having the user explicitly instruct the network to do so and so, okay? So this is the context awareness. Also, we have this distributed, can be distributed or central intelligence, okay? We are aware of the context without actually, we learn the context and then we are aware of it. And then we have the radio network aware system, okay? Knowledge of radio and network components environment models. So the system itself will learn about the environment models, and then it will learn about the structure, the architecture, deployment, and everything about the network. And this is through learning, okay? It's not actually pre-programmed. That's what actually the difference between these two, and then level 3, for example, is that the system is capable of that self-awareness. And then here in 4, the system is capable of planning. Okay, its system is it has its self-capability of planning to make its own plans. As I said, it's not pre-prescribed plans, but actually they are developed by the system itself. Analyze the situation, okay? It's able to analyze the environment, the situation, the context awareness, and then here it will determine the goals, for example, quality of service and power, and then it will follow a prescribed plan, but it's a general plan, okay? It's not a specific plan, it's generally optimize something, for example, or change the protocol so that and so, okay? So it has some objectives. And then number 5, the system is more intelligent, and now it's able to conduct negotiations. Okay, we negotiate the traffic, we negotiate the spectrum, we negotiate, for example, the deployment. So there is here negotiations. Okay, settlers a plan with the other or another radio network or a processing entity. Okay, so we try to be able to negotiate with other entities in the system. Okay, it can be a completely different network. Number 6, learns the environment, autonomously determines the environment structure. So here it's very important. We are not learning, for example, based on a specific model, like in channel identification, for example, we know that it's relay, then we will determine the relay parameter. We know it's a multipath, then we determine that. So here, actually, the system is completely free to determine here the environment structure, okay? That's really very powerful in terms of intelligence. And then adapts plans, okay? So here the system itself can generate new goals, completely new goals, okay? It's not, for example, something that the designer has set like goal 1, 2, 3. It can be something completely different and completely new, and the system designer has never thought of it, okay? So that's really very powerful in terms of intelligence, is that you set completely different new goals than what the system designer has even didn't think of. So this happens actually, this happens if, for example, there is a completely new environment that actually the designer has never thought of, okay? In that case, the network, as it is intelligent, it has to set up goals, given the environment, given the users, given what it has learned and so on. It will even come up with that, task, which is to propose new goals. And then here we adapt protocols, okay? Proposes and negotiates new protocols. So the whole protocol is completely new. For example, you have a MAC protocol with a specific, for example, frame format, specific fields, etc. Of course, this is impossible to change, for example, in any existing or even 5G or 6G network to change a protocol. So usually it's really very, very rigid, especially when it deals with the structure of the frame, for example, or the type of parameters. It says, okay, we can change, for example, parameters, but the protocol design is essentially the same. We can have some specific fields where we can adjust a little bit, etc. But essentially, the protocol remains very, very rigid as a structure. Okay. So here, the system in its top level of intelligence is able actually to change the protocols. Today, where are we? So I can say that we are at level 3. Okay, so this picture here is very futuristic in terms of cognition or cognitive networking. At the best, here we are at level 3, and 2 and 3 context awareness and radio or network awareness. Okay, so that's actually very very powerful, and we have this general architecture of intelligence or cognition. Okay, so now if we look at the cycle that I have presented before, it becomes a little bit more general. Okay, so we have here the external world. We'll observe it. Okay, we have this learning entity here. As Professor Awati said, so we have actually this cycle, which is observe, orient, plan, decide, and act. Okay, through a learning mechanism, where actually the system can actually adapt itself and adjust itself to the environment. So as I said here, the concept is at the network level and not necessarily based on the specific device. Okay, I think I have finished now this introduction about cognitive networking. So we can have a small discussion if you like. If there are any remarks before we go to the cognitive radio itself. So any remarks? Yes. I think we have the microphone. Yeah.
I may have not understood what you just said. I would like to know if in the coming generations we will be able to change the format of the packets or the frames, etc. I have not understood.
In the current protocols, we cannot
Yes.
do that. We cannot change it. It's very rigid.
Yes,
it's very,
we can only play on the free bits that are put on the header, for example, to put some information to. You understood?
Yes, you have
Yes.
fields, you have
Yes.
specific fields, and you use these. There are some protocols actually that can provision coexistence between protocols. For example, a version of a protocol that coexists with the previous version. So we keep the same number of bits or
Yes.
bytes, but in the newer version, the new bytes have a significance. For example, they mean something, but for the previous protocol, it's dumb. It doesn't mean anything. Okay, but the frame structure is rigid. Usually, it's very rigid. Okay, we may have some flexibility in 5G, for example, or nth G, but still, it's really very rigid.
Yes,
so we don't change usually protocols.
There are some ideas in the literature where we can focus on to find some clues to work on. Because I'm currently working on adding some information to the packet header in order to help the decoder to can extract information, etc. So I'm playing on the header entity. I'm adding some information.
You can.
Yes. I don't know what in the world what currently is. So I'm asking if it will be a good idea to think about changing some.
I think you misunderstood it.
Yes.
Actually, you can propose your own protocol. Okay, you
Yes,
can do whatever you want, and you come up with a new protocol. You say, okay, my header will be this of this length. I will add this field, and this field has this specific task, for example. Yes. You can do that, and it will be your protocol. Okay. But your protocol will not be necessarily compatible with existing protocols, because this will rely on standards. But you're right, that's what people do in research, right?
Okay.
What people do in research, what I will present later on, is that we come up with a new protocol, which is an improvement or something completely different. It has, it makes some advances in the field. And this is actually very appreciated to do it.
Yes, okay.
But what was meant here is that once you have a protocol, and you have a network that uses that protocol usually is kept the same. Okay? We may switch, for example, from different protocols. We can have some adaptivity, but a given protocol will not be completely changed.
Of course. Thanks.
Yeah. Yes.
Yes, as Professor Ibnkahla said, you can't change the protocol because or the stack, protocol stack. But you can, in the existing protocols and frames format, you have some free bits or free fields. So you can fill them with your information. You want to add something that you want to communicate to higher or down layers. But you need to standardize this so that the receiver can also understand what you send. Okay, this is one thing. Okay, this is the maximum that you can do currently. But if you want to, what Professor Ibnkahla said is to go to change the protocol. It could be, and I think it's possible, but it's through software-defined radio, and this is this thing that we need to add to cognitive radio is to have a radio or a network that is completely software. So then we receive the information from the environment, and we see, as Professor Ibnkahla said, that, by the way, I'm very happy to see for the first time this list of steps for the cognitive network, because this is what Metola called in his work, without defining it, the cognitive machine, the cognitive machine that you have in the heart of the cognition cycle. Okay, so this is nice to see all all this gathered in the same picture. So to come back to the flexibility or to changing the protocols. So imagine that I am in a given environment. I'm a device in a given environment, and I sense this environment, and I find that I have some quality of service that the current protocol stack cannot achieve. So what can I do? So what I can do is to download or to use another software protocol stack, to remove GSM and to replace it by 3G, because it's not hardware, it's software. So then the device that it becomes like a free box, we fill it with 3G. If it's okay, 2G I mean, if it's okay, does it. If not, I will fill it with the 3G, because it will help me to achieve the quality of service, the target quality of service. So there is a project that worked on this, which is end-to-end E2R, end-to-end reconfigurable radio. It was led by Motorola in 10 years ago. And the idea is that you have devices that there is nothing inside, but they download the appropriate or the relevant protocol stack, given the information that they have from the surrounding environment. Yeah, and this with software radio, you can do this.
Yeah, thank you very much. This is actually a very important addition to the discussion. Any other remarks? Actually, to add on this, actually, we have the concept of what Dr. Awatif said also. We have what we call cloud. So, did anyone hear about cloud computing? Computing. Okay. Now, cloud networking. Okay, so cloud networking. It's basically similar to the concept of cloud computing. So please keep your question later on, and I will come up to this one. Go ahead. You got the microphone?
Yes.
Okay, good.
In fact, I'm confused a little bit about the ad hoc notion. So what you mean by ad hoc means the feature that there is no infrastructure, or because when we say ad hoc connection, we say distance constraint. So I don't know, actually.
Yeah, actually, it's true. It's distance constraint, because the transmission range is usually limited. Okay, so actually the definition of an ad hoc network is not based on the distance. In fact, the distance is a consequence. The definition of ad hoc network is a set of devices that are in a given environment with infrastructure less, so they don't have, for example, base stations or anything. They have actually to self-organize and communicate. This is the exact definition. Now, why the distance is important is simply because the transmission range is usually limited. Okay, we don't want to interfere. We don't want to create interference and to the same network or to other networks. And also, usually it's based on multi-hopping. Okay, so to reach a device far away, we use multi-hopping. That's the definition.
Thank you.
Okay, so I'll come back to the networking, the cloud networking. So basically, this is actually a very brand new research. I think it started a couple of years ago. It's very, very recent. So basically, it's similar to cloud computing. Let's now talk about that. What everybody knows, cloud computing is that you have, for example, as users or as professionals or cities or municipalities. So anyone actually who doesn't have, computing facilities, they can actually have simple devices, very, very simple devices, and then these devices will upload the data to be processed to the cloud. The cloud will process it, and then it can get back to the users. Okay, so that you don't need actually to have the infrastructure, every user doesn't need to have the infrastructure for processing. Processing is actually done on the cloud. It's very flexible, very easy, from anywhere. It allows mobility, etc. And this is very important, for example, to convince people, for example, who want to install, for example, sensor networks or add, for any application, for example, for smart grid or for environment monitoring, we tell them that you don't need to have computers in your facility. For example, the city of Toronto, for example, we tell them, we sell you these devices, these sensor nodes, you deploy them in the city, and that's it. You don't need to have a professional or an engineer in the municipality, in your company, for example, to treat and process this information, so, or even store it. It's all done in the cloud. All what this municipality will do is just to pay a fee to the service provider, the owner of the cloud, which can be, for example, IBM or a big company that owns it. But that's actually very, very meaningless. It's not important. And also, anytime the user can actually cancel their subscription, and that's it. Okay, they don't need to handle computers and so on. So that's cloud computing. Now, the cloud networking, the concept actually is very similar. Okay, cloud networking, you have very simple devices, and you don't need actually to handle all the headache of the protocol stack. Like it can be even modulation, demodulation, or what you do, you have your raw data, you upload it to the cloud. The cloud will, of course, on packet switching concept, will process your packet, and you don't have to worry about it. Okay, so it will go to the destination, you transmit. So your device actually will be very, very light, very, very simple. It has very basic functions. It should have, of course, an antenna, probably an amplifier, of course, etc. But very, very simple things. For example, one thing, security can be done on the cloud. So a lot of things, enhanced coding, and etc. It can be done on the cloud. And your devices actually will be very simple. Now, as users, in that case, you can build your own. You can be an operator. Okay, you can decide to be an operator. Why? Because you simply don't need that infrastructure. The infrastructure is on the cloud. Okay, all what you need is very simple devices that you give to people. Tell them, well, I will sell you these devices. You belong to my network, and then you will not own base stations. You don't own anything. You just pay the owners of the cloud. Okay, you pay them a subscription, and if your company fails, for example, that's it. You cancel your subscription with the network cloud. Okay, so that's the concept. Now to go back to the protocols, the flexibility of protocols, this makes a lot of flexibilities in the protocols because you, as a device, you don't need to worry even about what protocol you'll be using. Okay, all what you need is to have matching between the data that will transmit to the cloud, and that's it. Okay, and in the cloud, of course, it's based on software technologies. Of course, you can have updates of the protocols and improvements and so on. Okay? Yes? Go ahead.
A new goal. What do you mean of a new goal in the... For example, for ad hoc network.
Yes, for example, let's say, for example, you have an ad hoc network functioning very well, okay? And then, all of a sudden, there is a problem, okay? It can be a natural problem, a disaster, God forbid, or a problem, okay? And that disaster, actually, the service provider has never thought of it, okay? Did never think that there will be, for example, an earthquake or flooding or something, okay? In that case, the network will be, for example, composed of only few nodes with minor capabilities in terms of computing, in terms of everything, and then there is an emergency situation. People are rushing, there is fire, there are a lot of things, etc. So what the intelligent network will do is to set new goals. Okay, I have to come out of this situation, I have to deliver packets, and my goal now is to deal with the situation, okay? So here, setting the new goals is a situation that the provider or the system designer has never thought of, and the system itself is intelligent to come up with. Like yourself, a human being is intelligent, so when a situation comes in, you never saw a lion, a real lion, okay? But if you see a lion in front of you, you will decide, okay? Now you don't know what to do, but when you see the lion, you will decide about it, okay?
So it is not only in terms of spectrum access or frequency use, so it will be for application.
It's very general. It's very general. It can be anything, actually, very, very general, okay?
Okay, thank you.
Yeah.
The light devices are located far away in the ad hoc network. So we need an authentication process and a key distribution mechanism to ensure a level of security in our networks. And in the cloud networks, on cloud computing, we have a distributed approach or a centralized approach for
It's distributed. It's distributed. In cloud computing, it's distributed.
Distributed
Yeah.
approach.
Yeah.
So, thank you.
Okay, so move on. Then, in that case, if there are no questions. So now I will move or go back actually to cognitive radio. So in the cognitive approaches in general, we said that we have to ensure that we have awareness of the system, of the network, etc. But in particular, there is a very important concept, which is cooperation. I think it has been discussed in the previous days over several angles. So cooperation actually, it's actually one illustration of intelligence. So devices and nodes, they cooperate together to ensure that actually they have a goal, which is to transmit packets to their final destination, and therefore they have to communicate, okay? So it's not simply relaying, okay? It's not simply relaying information, but it's much more than that. For example, in cognitive radio, the devices will learn about the environment, okay? So what they will do, they will cooperate, they will exchange that information together and help each other actually to have a better knowledge of the spectrum and of the environment. It can be, for example, channel identification. We know how the channels behave, and we communicate that information to our neighbors. We know who are the neighbors around us so that we can relay information and then communicate that information to other devices. So today we'll see some aspects of that. Simply here we are actually presenting the concepts that can be used. Now for the spectrum awareness, of course this is a very important task in cognitive radio. Here we have actually several ways to do it, okay? We have actually passive awareness, and then we have active awareness. I think yesterday Professor Awatif, she has discussed this as well. So passive awareness actually is information is dictated from a centralized processor about what are the spectrum bands that are available, okay? And the active awareness is actually the system actually is able to sense the environment and detect if there are primary users transmitting or not, okay? It's not only that we need to detect the transmitters, but also we need to detect, if possible, the location of the receivers, because we don't want actually to cause interference to the receiver. So that's actually very important. And in ad hoc networks, you want also to detect if there are other cognitive radio users at the same time, because you don't want to interfere with them, because this is an open access channel, okay? So every cognitive radio can have access to it, so we have to sense it to avoid collisions. That's very important, but also you need to explore and find out who will be your relays or your hubs, okay? In that case, your hubs also have to have the necessary spectral bands to transmit your information. So that's very important as well. And then, of course, you can have cooperative or non-cooperative approaches in terms of sensing. So now, what are the main problems or challenges about spectrum awareness, okay? So we have this problem of hidden terminal problem, okay? This is actually, I'm focusing on it here because in ad hoc networks it's really very important, okay? Imagine you are a set of cognitive radios that are transmitting, but actually you don't know whether there is a primary user transmitting or not, okay? Imagine, for example, you have here a primary transmitter transmitting to a primary user, okay? And you have a set of cognitive radios here, okay? So, so actually the range of the primary transmitter can be here, okay? It can be this one. So if the cognitive radio 1 here is trying to communicate with 2 or 3, it starts by sensing the environment, but of course it will not hear that actually the primary user is transmitting to the primary receiver, which is in the vicinity of the cognitive radio, okay, 1. So what will happen is that this one, CR1, actually will start transmitting, okay? And of course it will interfere with the primary receiver there. And this is actually what we call the hidden terminal problem, okay? Hidden terminal problem, we don't hear that there is a transmitter that is transmitting, even though actually we do our best to sense the environment, okay? Now, it's very important here to have cooperation between users, okay? For example, if this one is here, it's just in the border, so this one, CR3, actually can sense the primary user, okay? It's able actually to receive the signal from the primary user. Now, if there is, as I said, environment awareness between cognitive radio users and there is this collaboration, this one will provide its information to its neighbors. It will say, well, this band channel here is being occupied, refrain from transmitting and using it, okay? So this is where actually the cooperation can play a role. Now, I think also in terms of types of detectors, there are many possible detectors, and each of them has actually its strengths and also its drawbacks and its limitations. You have here the example of the energy detector and the matched filter, which are actually very well used and developed in many publications. Okay, now we can make a focus on cooperative sensing, okay? So as I said, the problem is often to get rid or to limit the problem of the hidden terminal problem, but also to improve the sensing of the environment. You have a question? Yes.
In cognitive radio, I mean in underlay, secondary users are allowed to transmit simultaneously with the primary user. So even though the secondary is detecting the primary signal, how could it be sure that it will not interfere with the receiver at the primary receiver side?
Yeah, actually, when you have the
it seems like the problem is to interfere with the receiver, the primary receiver, and not the primary transmitter.
Yes, but here you see the receiver. This is the receiver here, okay, primary user. So the transmitter is actually transmitting to the receiver here.
Yes.
Okay. So we don't hear the transmitter, okay?
Yes, yeah.
So this one, which is transmitting, doesn't hear that actually this one is receiving, okay? So the hidden terminal is this one, which is actually cannot be heard by.
Yes, this is in interweave.
Yeah. So the underlay, in the underlay. So I remind here. So the underlay means that you can transmit as long as you don't cause actually harmful interference to the device.
Sorry, to which device?
To the receiver, to the primary receiver, that's one. Yeah.
Ah, okay.
Yeah. So here we don't know because this cognitive radio, since for the cognitive radio there is no receiver, it will be able to transmit even at a high power. Okay, because it has sensed the environment. And it has no clue to know actually it is a harmful interference. Okay. So here in cooperative sensing, actually the devices will help each other, and of course they will enhance their detection probability, and also they can, by exchanging information, they can actually avoid the problem of the hidden terminal case. Okay, so how to cooperate? They can actually cooperate in a distributed manner or in a centralized cooperation. So in the centralized case, here, every node actually will send a set of results to a fusion center that we call fusion center, and the fusion center will make a decision, okay? It collects all information, and then according to some criteria, it can be, for example, the majority rule, for example, and it will decide whether there is a primary user present or not, okay? So that's the centralized cooperation, and then you have the distributed spectrum sensing, which means that actually the secondary users themselves, they exchange information together and then make decisions without having to go to a centralized entity to make these decisions. Okay, so that's the basic concept, which is actually very simple, and there are a lot of varieties in doing it. Okay, so now there are actually two ways for sensing. You can actually sense one single band, okay, and then go to the next single band and make decisions, or you can choose the multi-band concept, okay? Multi-band means that you actually sense a large band of, or a large number of channels, okay? And then you can rank them, the best channel and the second best, etc. And then you make your decisions, okay? And once one of them, for example, becomes occupied, then you move to the next one that you have at hand, okay? So if we look at the single band, it is actually very simple, okay? But actually to detect a new channel, it can take time because actually you don't have many of them. You just sense one at a time, okay? So that's the problem with it. But as I said, for multiband, you have actually a set of channels that are available, but actually this methodology here, it's a little bit more complicated, okay? So as you see here, you have only frequency, okay, one single band, and here you have a bunch of or a large set of channels. Okay, I think here the spectrum access has been also decided or discussed yesterday. So the basic or two basic ones, we have the spectrum underlay and spectrum overlay, which is which are actually used. So we have for the overlay actually you access the channel only if the user is not present. Okay. In that case, it's flexible in terms of power control because you are not actually causing harmful interference to the user. It gives flexible transmission range as well. And then it doesn't cause interference to the users, to the primary users, as long as the detection is good. Okay. Now, for the spectrum underlay here, it's good because it allows you, or it allows the cognitive radio users to have actually, better throughput because it has more available channels, etc. But the problem is that it can actually cause interference, and it needs a lot of power control, which is actually, not always easy to undertake. Okay, so now in terms of cooperative communications, we have actually a lot of flexibilities. We can have what we call the cognitive relay network. So actually, the whole network actually is based on the access technology which is adopted, and then actually they can transmit in a cooperative manner. However, we have also the other way of doing things, which is actually we can have the space-time frequency coding example where actually you can exploit the time, you can exploit the frequency, you can exploit also the beam, the space. So it's really very, very flexible if you can make use of all of them. I think the previous days also we have seen these examples. So here before the break, I will just make some comments between the single band and the multi-band approaches. So for the single band, as I said, we have this technology which is actually faster. So if you look at this diagram here, the cognitive radio actually will listen to the channel, and then it will discover one spectrum hole, and then if there is success, then it will have access to it. So it doesn't have any choice, just one choice, and so on. And of course, as I mentioned here, the problem is the probability of communication loss is if the primary user comes back to reclaim its own channel. However, for the multi-band case, actually you have sensing of multiple bands. Okay, and in that case, as I said, you will rank them, and then you make use of one of them. And then, of course, we have the spectrum sharing, which means that if you have a set of cognitive radio users, as we see later on for cognitive ad hoc networks, you can actually allocate the spectrum according to the needs of each user. Okay, I think when do we have to stop for? Is it soon or?
10:30.
10:30. Okay. I think we have. Yeah, because we start the new or the second part, which is actually about our exact problem, and we'll finish it, or we start it the next half. Okay. I